So the first fundamental theorem of calculus states the following. If capital F of x, so this is uppercase, is the antiderivative of f of x, this is lowercase, then the following is true. The integral from a to b of f of x, this is lowercase, dx equals capital F of b minus capital F of a. So what this is really saying is it's the same as saying that the area under a curve, which is what we're really talking about over here, so it's the area under the lowercase f of x from a to b is the change in its antiderivative capital F of x from a to b. And we've actually worked with this extensively already. It's nothing particularly new. Because what we were saying is we were saying that if this is lowercase f of x, and that's a, that's b, we have some sort of shape here, and this area here is 2, that this area here is the same as the change in capital F from a to b. That basically if this area is 2, then this went up 2 from a to b. And this idea is so important because it's where two branches of calculus merge. We spent all this time finding the derivative, finding the slope of the tangent line. And then we spent all this time finding the area, using little Riemann sums to estimate the area overall. And now this fundamental theorem of calculus, and it's so important it's called that fundamental theorem, says that we can put those two things together. If we're looking for the area under the curve and we have an equation for lowercase f of x, if we can take the antiderivative using those techniques that we worked with earlier, if we can find that antiderivative, then we can just plug in these numbers and subtract them, and boom, there's our answer. We don't have to do Riemann sums anymore. And previously when we worked with this, we were using this fact that, like say this was the velocity curve, that if we found the area under the velocity curve, that would give us the change in position. We were trying to find something about the change in position graph. Now what we're doing though is we're going the other way. We're using our knowledge of essentially the equation for the position graph to figure out the exact area under the curve of the velocity graph. You'll notice this capital F and this lowercase f. This is a fairly common convention that you'll see that a capital letter is used for the antiderivative and the lowercase letter is used for the derivative. It's a little bit tough with my handwriting to tell which is which, so I'm going to try to be really careful with it. So what we're going to be seeing now are problems similar to ones we were doing with Riemann sums. So let's say find the antiderivative, or the integral from 1 to 3 of x squared dx. Except now instead of estimating it using Riemann sums, we're going to find the exact value. So I'm going to write out some steps for how we're going to do these problems. They're the same always. First, we're going to take the antiderivative. Then we're going to write our bounds. So the bounds are the numbers right here. Then we're going to substitute the bounds. Substitute into the antiderivative. And subtract. We always do the upper minus the lower. Even if the upper one is actually smaller, we're still always going to do the upper one, whatever one's up here, minus whatever one's down here. And then the fourth thing we're going to do is check on the calculator. If it's available. And the way that we're going to check on the calculator is we go to Math, 9, it says finite integral. And then we're going to have an expression that's going to look like this. It's going to be finite integral. And we're going to do the original expression, variable, lower bound, and upper bound. Notice here we're always going to do the upper bound minus the lower bound. In the finite integral, we're going from smallest to largest, from the lower bound to the upper bound. So let's look at how that comes out. So right here, the first thing we're going to do is we're going to take the antiderivative. So the antiderivative of x squared, we add 1 to the exponent, divide by the new exponent. And one of the things that's very confusing is that when we do this, we aren't going to write a plus c. When we're doing an indefinite integral or an antiderivative, normally we have that plus c. If we're doing it with the numbers in it, though, when we do our subtraction in the middle, where the plus c's are going to subtract out, so we actually don't have to put it in originally. If you do, it's not wrong, it's just extra. So this is the antiderivative. And then what we're going to do is we're going to write our bounds. There are two notations. One is that you'll just see this line with a 1, 3. You'll also sometimes see this as a little bracket like that with a 1 for the lower bound, 3 for the upper bound. In either case, this is going to be the upper bound. This is going to be the lower bound. Okay, the next thing that we're going to do is we're going to substitute the bounds into the antiderivative and subtract. Make sure you have parentheses when you do this, especially if there's any addition or subtraction in the antiderivative. So we're going to substitute in 3 cubed over 3. Make sure your substitution's in parentheses. Subtract 1 cubed over 3. And all we have to do now is that simplification. So 3 cubed is 27 over 3, minus 1 cubed is 1 over 3, giving us 26 thirds. Now what I'm going to do to check that, get out my calculator, math, and then if I go all the way down here to 9, that's finite integral. So I'm going to put in my original equation. So I can check this just by having this, if I cover up all the other work that I've done. So first thing I'm going to put in is that expression, x squared. Then my variable, which is x. I'll make it a little darker. Then I'm going to put in my lower bound first, then the upper bound, close parentheses. Right like that. Now if I turn that into a fraction, should end up exactly what I got before, which it does. So good. We check that off. The remainder of this lecture is just showing you a bunch of different examples. It is really important for this to be able to take the antiderivative accurately. If you can't do that, you really have to go and brush up on it. So for our second problem, let's find the integral from -1 to 4 of x plus 5 dx. I want to show you this one because I want you to see how you need to work with addition really carefully when doing these problems. So the first thing that we're going to do in our steps is we're going to take the antiderivative, so that's x squared over 2 plus 5x. Again, this has to be very automatic. And we're going to put in our bounds from -1 to 4. This is why I like to use this notation with the brackets, because it says this whole thing is our antiderivative. So then we substitute this into both of these. So whole thing, 4 squared over 2 plus 5 times 4. Then we're going to subtract this -1 substituted into the whole thing. Don't lose track of your negative right here. This simplifies to 28 minus -4.5, which gives us 32.5. Again, with our calculator, math 9, work with the original expression, $32.5. For ones like this, you really have to be able to take the antiderivative accurately. What I'm going to do with this is I'm first going to have to rewrite before taking my antiderivative. Remember, you need to keep your rewrite steps distinct from your other steps. So I'm actually just going to do the rewrite steps over here, and then I'm going to do the antiderivative over here. So this is the same as the integral from 2 to 3, x to the -3 dx. When I take that antiderivative, I add 1 to the exponent, divide by the new exponent, write my bounds. Now, it's hard to evaluate numbers that have a negative exponent, so I'm going to rewrite this again. Notice I haven't done the substitution, so I still have all this. And now I'm going to put in my bounds, do that substitution. Simplify. So subtracting a negative gives us a positive. I can find common denominators. Oops, this is over 72. There we are. When I put this back in, there we are. And that's correct. You should also be able to evaluate when you have things like e or trigonometric functions. So if we're doing the integral from 0 to 2 of e to the x plus 4 dx, going to do our antiderivative of e to the x is just e to the x plus 4x. We're going from 0 to 2. When we substitute this in, we have e squared plus 4 times 2. All of that minus e to the 0. We're putting in that 0. So we have e squared plus 8 minus anything to the 0 power is 1. 4 times 0 is 0. Make sure you distribute that negative, although the 0 goes away. Check it. E to the x plus 4 comma x comma 0 comma 2. Now we can't do math fraction because it's not a math fraction, because it's not a fraction over here. But I can do putting this in to see what decimal I get. So e squared plus 7. Same thing. It's exactly what we should get. Probably the hardest ones are the trigonometric functions. Let's find the integral from 0 to pi of sine x dx. So remember, we're doing the antiderivative, so we're going to go this way. So this is negative cosine of x. Our bounds are 0 to pi. So we're going to do negative cosine of pi minus negative cosine of 0. You just got to know how to evaluate these puppies. So here, when x is pi, we've got the point negative 1, 0. When x is 0, we have the point 1 comma 0. So cosine is the x value. That means the cosine of pi is negative 1. So we have a negative 1 minus a negative cosine of 0 is just positive 1. So make sure you watch out for those negatives. Those two negatives get together to be a positive. 1 plus 1 is 2. When we check it here, make sure you're in radians first. This radians should be highlighted. Math 9, sine of x, comma 0, comma pi. Remember, your pi button is right above the caret. There we go. 2. And our final one is just showing you how sometimes we have those rewrite steps still in here. So let's do the integral from 1 to 2, x squared plus 1 over x dx. And let's keep our rewrite steps over here before we do our integral steps over here. So this is the same as saying this is the integral from 1 to 2. We can see that this exponent is bigger than this one, so we can split up this fraction. And if we simplify that, we have the integral from 1 to 2 of x plus 1 over x dx. If we take that antiderivative, we get x squared, add 1 to the exponent, divided by 2. Then you just have to remember, the antiderivative of 1 over x is the natural log of x. We're going from 1 to 2. So 2 squared over 2 plus the natural log of 2 minus 1 squared over 2 plus the natural log of 1. So 2 squared is 4, divided by 2 is 2. So it's 1/2. Another thing you just gotta know, the natural log of 1 is 0. You can do it on your calculator and confirm. But this is one of those facts that ends up coming up a lot on the AP test. Basically what we're saying here is that e to the what power equals 1, well anything to the 0 power gives us 1, so the natural log of 1 is 0. So we have 2 plus natural log of 2 minus 1/2 minus 0, 1.5 plus the natural log of 2.